Okay, so let's unpack this right away. I want you to picture a number. And I don't mean a normal big number, like the national debt or the number of stars in the galaxy. Those are cute. Those are frankly adorable.
They really are. I mean, they're practically zero in the grand scheme of things.
Exactly. I want you to imagine a number so catastrophically, mind-bendingly colossal that if you tried to hold just the digits of it in your mind.
Just the digits.
Right, just the digits. If you tried to physically encode that much information into the neurons of your brain, your head would literally collapse into a black hole.
And just to be absolutely clear for everyone listening, that is not a metaphor. We aren't being poetic here.
No, it's actual physics.
It is. It's a calculation based on the Bekenstein bound, which basically dictates the maximum amount of information you can cram into a finite region of space given its energy. If you pack too much information, too much entropy into the volume of a human skull,
the density exceeds the Schwarzschild radius.
Exactly. You become a singularity. Poof.
So we are talking about numbers that are physically dangerous to think about in their entirety. We are talking about hyper-large numbers, the absolute heavyweights of the math world, specifically things like Graham's number.
Graham's number is the poster child for this whole concept. It's a number so large that the entire observable universe is far, far too small to write it down, even if you wrote a single digit on every single Planck volume.
Which is the smallest measurable unit of space.
Right. You'd run out of universe before you even made a dent in Graham's number.
But here's the hook. Here is the paradox that makes this deep dive today so fascinating. Even though this number is too big for the universe to contain, and even though it defies all standard scientific notation, we actually know exactly how it ends.
We do. We know the last digit. We know the last 10 digits. We know the last billion digits, actually.
It turns out that at the very, very bottom of these infinite towers of sheer mathematical chaos, there is a rigid, totally deterministic structure, a pattern that just locks into place.
It's a phenomenon mathematicians call frozen digits, or sometimes you'll hear it called stable digits.
So welcome to the deep dive. Today, we are going on a serious journey into the infinite. We are unpacking a stack of pretty dense research papers, very heavy on the number theory, primarily focusing on the incredible collaborative work of EnigMatematica and mathematician Marco Ripà.
Right, their work on the mathematics of tetration.
Tetration, which we'll define in a second. But our mission today is to solve a very specific mystery. How can a mathematical operation that explodes towards infinity, adding trillions of digits a millisecond, somehow settle down into a predictable, frozen pattern at the very tail end?
And more importantly, can we measure the speed of that stability? Because that is the key contribution of the source material we are looking at today. Ripà and his colleagues at EnigMatematica didn't just notice the pattern. They found the speedometer. They developed a metric called congruence speed.
Denoted as V of A.
Right, V of A.
This metric basically tells us the speed limit of the number system itself. It's a story that takes us from basic arithmetic, which we all know, straight into the weird underground world of p-adic analysis, modular arithmetic.
And eventually a really deep philosophical question about whether we are inventing numbers when we do this math, or just discovering locations on a map that has literally always been there.
It bridges the gap between total chaos and absolute order. So buckle up. We are looking for order in the infinite today.
Let's dive in.
Okay, so to understand the end of the universe, or at least the end of these monster numbers, we have to understand how they are built in the first place. We need to talk about the ladder of operations.
Right. Most listeners probably know the first three rungs of this ladder perfectly well. You learn them in elementary school.
Sure. Rung 1 is addition. That's just repeated counting. 3 plus 3.
Simple enough. Then rung 2 is multiplication, which is just repeated addition. 3 times 4 is really just 3 added to itself 4 times.
Right. 3 plus 3 plus 3 plus 3. Then rung 3 is exponentiation, which is repeated multiplication. 3 to the 4th power is 3 times 3 times 3 times 3.
But the ladder keeps going, and this is exactly where most people get off the bus. Today we are talking about the 4th rung, tetration.
Tetration.
The word itself comes from tetra, meaning 4, and iteration. It is iterated exponentiation.
Visually, if you're reading a math paper, this is usually written as a little superscript number to the left of the base. So a small b followed by a big A. We read that as tetration of height b with base A, or sometimes b tetrated to A.
Correct. So A is the base, the actual number you're multiplying, and B is the height of the tower.
And I really want to emphasize that word tower for you listening, because if I see a little 4 to the left of a 3, That is not 3 times 4. It's not even 3 to the 4th power, which is just 81.
Oh, no. 4 tetrated to 3 is a tower of threes. It is 3 raised to the power of 3, raised to the power of 3, raised to the power of 3.
And crucially, and this is where I always get tripped up when I try to do this on a napkin, you have to evaluate it from the top down.
You absolutely have to.
Yeah.
If you did it bottom up, it would just collapse into a slightly larger standard exponent. To get the true scale of tetration, you start at the penthouse and work your way down to the lobby.
Let's walk through that just to give the listener a true sense of the vertigo involved here.
Right.
Let's take that exact example. 4 tetrated to 3, height 4, base 3. The very top of the tower is 3 to the 3rd power.
Which is 27.
Okay, 27. Easy enough.
Yeah.
So now the tower is one step shorter. Now we take the next 3 down and we raise it to the 27th power.
And this is where we are already leaving the realm of human intuition. 3 to the 27th power is roughly 7.6 trillion. Specifically, 7,625,597,484,987.
Okay, 7.6 trillion. That is a massive number. That's the national debt of a medium-sized country right there. But I can still somewhat hold that concept in my head. But we aren't done. We still have one more step. We have the bottom 3.
Exactly. Now you have to calculate 3 raised to the power of 7.6 trillion.
And that is, I mean, what even is that?
It is a number with roughly 3.6 trillion digits. Not the value, the number of digits.
Trillion digits.
Yes. If you printed that number out in a standard 12-point font on normal paper, the stack of paper would reach from the Earth to the moon and back multiple times. Or if you laid the pages out flat side by side, it would wrap around the equator hundreds of times over.
And that was just height 4.
Just height 4. That is a baby tower. That's nothing.
So when we talk about Graham's number,
Well, Graham's numbers is defined using Knuth's up-arrow notation, which introduces a whole other beast of recursion. But fundamentally, underneath all that notation, it represents a power tower of 3s, where the height itself is a number so big the universe breaks just trying to express the height.
right, so we are effectively dealing with power towers of infinite height.
For all practical purposes, yes. Infinite.
So it's a tower that just never stops growing. It's reaching up forever. Now, normally, when we think of things growing that fast, that kind of explosive runaway growth, we think of pure chaos.
You think of entropy.
Yeah, exactly. You would assume that as you add another power of 3 to the very top, the digits at the bottom would just be churning like a blender. Everything shifting left, everything changing constantly.
That is definitely the intuition. But math is full of completely counterintuitive surprises.
Because what the research shows, and this is so central to Marco Ripà's work with EnigMatematica, is that as the tower gets higher and higher, the digits on the far right-hand side, the smallest values, they just stop moving.
This is the phenomenon of frozen digits.
It is exactly like pouring concrete.
That is a really great analogy, actually.
The top of the tower is still wet cement, being poured by the truck, building higher and higher floors. It's fluid, it's constantly changing. But the bottom, the foundation, it cures, it hardens, it sets into absolute stone.
And once it sets, it never changes again. No matter how incredibly high you build the top of that tower, the bottom logic is completely locked in.
Let's look at a simpler example straight from the source material to help visualize this. Base 5.
Base 5 is a classic starting point because it stabilizes very visibly and very quickly. Let's look at the sequence.
Okay.
Height 1 is just 5. Simple. Height 2 is 5 to the 5th power. That's 3,125.
Okay, so the last digit is 5.
Right. Now, height 3 is 5 to the power of 3,125. Now, that is a huge number. We can't write the whole thing. But if you calculate the tail end of it, it ends in 874,21875.
Okay, let's look at it again there. It ends in 5.
It does. But look at the digit right before the 5. In the previous step, 3,125, it was a 2. In this new massive step, it is still a 2.
And the digit before that?
It's a 1, so it ends in 125.
And if we go to height 4?
It will end in 3125.
So the 5 locked in. Then the 2 locked in. Then the 1 locked in. Then the 3 locked in.
Precisely. It is like a zipper, slowly closing from right to left. As the height, the B value, increases, a wave of frozen stability creeps from the right side of the number to the left. Once a digit freezes, it is permanent. It is etched into the fabric of the math itself.
And this is exactly what allows us to know the last digits of Graham's number. because Graham's number is essentially a power tower of threes that is so unimaginably high that a huge chunk of the bottom digits have just frozen solid.
Yes. We absolutely cannot see the top of the tower. It's lost in the clouds of infinity, but we can stand right there in the lobby and look at the serial number carved into the cornerstone, and we can read it perfectly.
Okay, so we know that they freeze. That phenomenon has been known for a while, right? That isn't entirely new news.
Right. I mean, Euler knew about the structure to some extent centuries ago.
But the much deeper question, and the real focus of the EnigMatematica collaboration, is how fast.
Exactly. Is it 1 digit per step, 10 digits per step? Does it accelerate? Does it stall out? Is it just completely random?
And this brings us to the main character of our deep dive today, a metric called congruence speed.
Denoted in all the papers as V of A.
V of A. It sounds like a velocity.
It is a velocity in a way. It represents the literal rate of freezing. V of A tells us exactly how many new stable digits we gain for every single step we add to the height of the power tower.
So if V of A is 1, we gain 1 frozen digit per step. If it's 5, we gain 5 frozen digits per step.
Roughly, yes. That's the practical translation. And the major discovery in these papers, the real aha moment of Ripà's work, is that for a sufficiently large height,
The speed becomes constant.
it stops fluctuating wildly. It just settles into a specific, predictable integer value.
So we aren't just guessing anymore. We can actually calculate this speed ahead of time. But how? What actually determines if a number freezes quickly or slowly? Why is base 5 supposedly faster than base 3? Or is it?
This is where we have to lift the hood. We have to look at the engine of the number system itself. We have to look at the factors.
We are talking about p-adic valuation.
We are the Greek letter nu sub p.
Okay, let's unpack p-adic valuation, because honestly, it sounds like something you need a PhD in advanced topology to understand. But reading through the source material, I have a feeling you can explain it to us in fairly plain English.
It is actually very intuitive once you force yourself to change your perspective on what numbers actually are. Usually when we do math, we care about magnitude. We care about how big a number is. 50 is bigger than 40.
Right, size matters in standard math.
Exactly. But in p-adic analysis, we do not care about size at all. We care about divisibility.
We care about what the number is made of, the ingredients.
Exactly. We care about its DNA. In our standard decimal numeral system base, 10, the fundamental building blocks are the prime numbers 2 and 5, because 2 times 5 equals 10.
Right. Those are the atomic parents of 10.
So a p-adic valuation simply asks a basic question. How many times can I divide this specific number by a prime p? Let's take the number 40, for example.
Okay, 40.
40 is 8 times 5. Or, written with primes, it's 2 to the third power times 5 to the first power.
Got it.
So the 5-adic valuation of 40 is 1, because there is exactly 1 5 in the prime factorization.
Okay.
And the 2-adic valuation of 40 is 3, because 2 to the third power is 8, and 8 divides 40 perfectly.
Okay, that actually is simple enough. It's really just counting prime factors.
Oh.
It's like doing a genetic test on the number 40 and counting how many 2 chromosomes and 5 chromosomes it has.
That is exactly what it is.
But how on earth does counting prime factors connect to the speed of these frozen digits at the bottom of an infinite tower?
Well, the congruence speed, that V of A, comes directly from these valuations. Specifically, Marco Ripà's formulas show that the speed depends on how many times you can divide the neighbors of the base by these primes.
The neighbors, you mean like a -1 and a +1?
Yes. Trivial manipulations of the base. Or sometimes even a squared plus 1.
This is genuinely fascinating to me. So to find out how stable a huge power tower of a specific number is going to be, you don't actually look at the number itself. You look at the guys living next door on the number line.
You look at its trivial manipulations, exactly. Ripà categorizes these into what he calls congruence classes. He breaks the whole system down based on what the base number is modulo 20.
Modulo 20, which for anyone rusty on their modular arithmetic, is basically just asking what the remainder is when you divide the number by 20.
Correct. So let's look at case 1 from the paper. Suppose your base, A, ends in 1, like 21 or 41 or 101.
Okay.
If you subtract 1, so a -1, what happens to those numbers?
Well, 21 becomes 20, 41 becomes 40. They all end in 0.
Which means they suddenly become multiples of 10. They suddenly have those magic factors of 2 and 5. Ripà found that for these numbers, the congruence speed largely depends on how divisible that a -1 neighbor is by those specific primes.
So the secret to the infinite stability of 21 is actually hidden inside the number 20.
Exactly. It's hiding in plain sight.
Okay, but what about numbers that don't end in 1? What about the tricky ones?
The trickiest ones, mathematically speaking here, are numbers ending in 3 or 7, like 3, 13, 7, 17. This is classified as case 3 in the literature.
Okay.
For these bases, simply subtracting 1 or adding 1 doesn't help us at all. Take 3. 3 minus 1 is 2. That is not divisible by 5. No good.
Right.
3 plus 1 is 4. Also not divisible by 5. Still no good.
So how do we find the hidden factors of 10 for a number like 3?
We have to work a little harder. We have to square it. What is 3 squared?
Right.
And what is the immediate right neighbor of 9?
9 plus 1 is 10.
Bingo. For bases ending in 3 or 7, the congruence speed depends on the p-adic valuation of a squared plus 1.
A squared plus 1. Why that specific formula, though? Why square it?
Because if any number ends in 3 or 7, its square will inevitably end in 9. 3 squared is 9, 7 squared is 49, 13 squared is 169.
Ah, I see it.
And adding 1 to any number ending in 9 gives you a number ending in 0. It neatly brings you right back to the magic factors of 10.
So the DNA of stability, the blueprint for how fast it freezes, is hidden in how easily you can mathematically turn the base, or its square, into a multiple of 10.
That is a brilliant way to put it.
Yeah.
We are essentially looking for the path of least mathematical resistance to the prime factors 2 and 5.
Okay, let's actually apply this. Let's do the math. We started this whole deep dive with Graham's number, the biggest celebrity in math.
Right.
Graham's number is fundamentally a tower of 3s. So our base is A equals 3.
Right.
So we need to find the congruence speed of 3. We need V of 3.
Let's apply Ripà's formula live right now. Since 3 is congruent to 3 modulo 10 and modulo 20, we fall squarely into that case 3 we just talked about. So we look at a squared plus 1.
Okay, so 3 squared plus 1, that's 9 plus 1, which is 10.
Now we need the p-adic valuation of 10. Remember, how many times does 5 divide 10?
Just the ones. 10 is 2 times 5 to the first power.
Correct. So the p-adic valuation is simply 1.
Which means V of 3 equals 1.
Precisely 1.
So a power tower of 3s, essentially the core architecture of Graham's number, gains exactly 1 new stable digit for every single step you go up the tower height.
It is a very slow, very steady march. 1 digit at a time, it is perfectly linear.
That is incredible precision for something so fast. So Graham's number is, well, the top layer is often simplified as 64 tetrated to 3, roughly, in terms of the stage of the recursion we're talking about.
Roughly, yes, to give us a working model.
So Ripà's work formally proves that Graham's number shares exactly, wait, what was the exact term of the paper?
It shares exactly slog base 3 of g minus 1 stable digits with the infinite power tower.
Break that down for us, slog base 3.
The slog, or superlogarithm, is basically the inverse of tetration. It counts the height of the tower. Since the congruence speed V of 3 is exactly 1, the number of frozen digits is essentially equal to the height of the tower itself, minus 1.
So if the speed was 2, we'd have twice as many frozen digits as the height.
Exactly. If V of O is 2, you'd multiply that height by 2. But for base 3, it's a 1-to-1 ratio.
But wait, the source material mentions something else about the tail of Graham's number that caught my eye. It mentions a phase shift.
Ah, yes. The asymptotic phase shift. This is where we get into the digits that haven't frozen yet.
Right, because if I have a frozen tail of, say, 500 completely stable digits, there's a 501st digit just to the left of that wall that is still changing as the tower grows. It's on the borderline.
Correct. It's the active frontier. And the obvious question is that frontier entirely random? Is the math just rolling a 10-sided die every single time we add a power to the top?
And the answer is no.
The answer is absolutely no. Ripà and EnigMatematica found that the digit just to the left of the frozen tail actually cycles.
It cycles. You mean like a predictable pattern?
It toggles. For base 3, specifically, the difference between the non-stable digits of consecutive heights flips back and forth.
Flips between what values?
Between 4 and 6.
Just 4 and 6. Back and forth forever.
It is a strictly modular pattern. The paper describes this asymptotic phase shift in detail. For base 3, the sequence of these shifts is 4, then 6, then 4, then 6, to infinity. It just bounces back and forth like a metronome ticking outside the frozen wall.
That is wild to think about. So even the so-called chaos just outside the frozen digits has a heartbeat.
Exactly. We literally cannot write Graham's number down in our physical universe, but we can describe its tail with absolute mathematical precision. And we can even describe the behavior of the digits just beyond the tail. We have a perfect map of the very edge of the number.
That is what I love about this research. It makes this terrifying monster number feel almost tame. Like we have successfully captured it in a cage of modular arithmetic.
We have certainly constrained its behavior. We've proven it still has to follow laws.
Okay, so we figured out the speed of base 3. It's slow. V of 3 is 1. But the papers dedicate a lot of time to what they call an inverse problem.
Yes, the inverse construction.
Meaning, instead of taking a random number and trying to find its speed, can we actually build a number that has a specific speed? Like, if I want a base number that freezes 100 digits per step, can I engineer one?
You absolutely can. And this relates directly to the study of perfect powers.
Perfect powers, like perfect squares, perfect cubes.
Yes, numbers of the general form x to the power of c. The research shows a completely fascinating relationship between that exponent c and the resulting congruence speed.
Go on. How does it work?
Ripà mathematically proves that for literally any integer c, you can find infinitely many base numbers that are c-8 powers and have a congruence speed exactly equal to c.
So if I want a speed of 5, I should just look for perfect fifth powers.
Essentially, yes, though there is a very specific algebraic construction mentioned in the papers to guarantee it. It looks something like 10 to the power of k plus t plus 10 to the power of t plus 1, all of that raised to the power of c.
Whoa, okay. Let's decode that formula a bit for the listener. 10 to a power plus 10 to a power plus 1, all raised to c. It looks scary on paper, but what is it actually doing mechanically?
Look at the internal structure inside those parentheses. It's a number constructed entirely of ones and zeros, powers of 10 plus 1 at the end.
Right.
This specific, highly engineered structure ensures that when you look at those p-adic valuations, those counts of prime factors we talked about, they are perfectly aligned.
So you are basically handcrafting a base number that is perfectly divisible by exactly the prime factors you need it to be divisible by.
Exactly. You're stacking the deck. And when you finally raise that entire parenthesis structure to the power of c, you effectively multiply those carefully aligned valuations by c. So you are mathematically, rigorously guaranteeing that the final congruence speed will be exactly c.
So we really can engineer numbers to freeze at whatever rate we want. We can build custom high-speed numbers.
Within certain boundaries, yes. It perfectly highlights that this freezing effect isn't some magical, isolated property of the number 3 or the number 5. It is a fundamental structural property of how the base interacts with the numeral system itself.
Speaking of the numeral system, this brings us to what I think is one of the most mind-bending parts of this entire deep dive. The environment matters.
The radix.
The radix, right? We use base 10. Humans have 10 fingers, so we develop base 10. And in base 10, tetration seems to behave pretty well. It stabilizes, it freezes.
It behaves specifically because base 10 is what we call square-free.
Square-free. Define that for us simply.
A number is square-free if it is not divisible by any perfect square other than 1.
Okay.
So look at our base, 10. Its prime factors are 2 and 5, 2 times 5. Are there any squared primes in there?
No.
Just distinct primes, 1, 2, 1, 5. Distinct primes. Now look at base 6, 2 times 3. Again, distinct primes. It is square-free.
Okay, so what is an example of a non-square-free number?
Look at base 4. 4 is literally 2 squared. It is a square. Or look at base 12. 12 is 4 times 3, which is 2 squared times 3. It contains a square factor.
The 2 squared.
Right. Or consider base 16, which computer scientists love, hexadecimal. 16 is 2 to the 4th power. It is a square of a square.
And according to Ripà's work, this distinction between square-free bases and non-square-free bases makes a massive difference in how tetration behaves.
A critical, fundamental difference. In a square-free system like our everyday base 10, stability is robust. Almost every single base number you try will eventually freeze its digits at a constant speed. It is a stable mathematical universe.
But in a non-square-free system,
Stability is incredibly fragile.
how fragile are we talking?
Well, there is a specific rule in the papers involving the radical. The radical of a number r, denoted as rad of r, is simply the product of its distinct prime factors, ignoring any exponents.
So for base 16, which is 2 to the 4th, the only distinct prime factor is just 2. So the radical of 16 is just 2.
Correct. Now, here is the instability criterion they discovered. In any non-square-free radix R, if your tetration base A happens to be divisible by that radical, the congruence speed never stabilizes.
Never. It never freezes into a constant rate.
Never. It accelerates completely out of control.
Whoa. Let's trace that out. Let's imagine we are alien beings with 16 fingers, and we natively count in hexadecimal base 16.
Okay, a base 16 universe.
And I pick a base for my tetration, let's say 2, because 2 is divisible by the radical of 16, which we said was 2.
Right.
So I start building a power tower of 2s in this base 16 alien world. What actually happens to the digits?
The number of stable digits, which would be the trailing zeros in this case, grows explosively. It does not settle into a nice constant rate like 1 digit per step.
So what does it do?
It might give you 1 zero on the first step, then jump to 4 zeros, then 20 zeros, then 100 zeros.
It effectively crashes the system.
It causes absolute chaos in the congruence calculations. The zeros accumulate so unbelievably fast that the p-adic valuation never settles down to a flat line. It just keeps jumping exponentially.
So Graham's number,
Mm-hmm.
which is a tower based on 3. In our base 10 world, it freezes nicely. But if we tried to calculate a tower of 2s in base 16,
You would not find that nice, linear, predictable tail. You would find a runaway train. The speedometer would just spin faster and faster until the needle broke off.
and Ripà makes a pretty bold conjecture about this in the material, doesn't he?
He does. He explicitly conjectures that square-freeness is the sole criterion. He suspects that only in square-free numeral systems do you get this ironclad guarantee of constant speed for all bases.
That is profound. It basically suggests that our entire ability to predict the tail of a monster like Graham's number relies heavily on the totally arbitrary biological fact that we have 10 fingers and count in base 10.
Exactly.
If we had evolved to count in base 8 or base 16, the math of infinite numbers would look like a completely different, much more chaotic landscape.
It absolutely implies that this stability isn't purely a property of the number itself, but a property of the specific lens we happen to be viewing it through.
Okay, speaking of the philosophical implications,
Yeah.
we have spent a lot of time talking about the how, the formulas, the congruence speeds, the bases, the radiuses, but we haven't really touched on the deeper why.
The why is my favorite part of all this.
I knew it would be. Because why does the number freeze at all? Why doesn't it just keep churning out random digits forever, even in base 10? What is physically or mathematically stopping it?
Because it forces us to look at numbers not just as quantities that grow, but as physical locations.
The locations.
Think about it. We usually think of a power tower as getting bigger and bigger, rushing endlessly towards positive infinity. It's moving constantly to the right on the standard number line.
Right.
But in the p-adic sense, in the realm of factors and valuations,
Yeah.
it is actually rushing towards a very specific point.
A fixed point.
Exactly, an attractor. We need to introduce the concept of the p-adic integers, specifically denoted as z subscript 10 for our base 10.
How is a p-adic integer different from a regular integer I use every day?
Well, a regular integer is a finite string of digits, 1, 2, 3, or 5, 8, 4, it stops. But a p-adic integer can extend infinitely to the left.
To the left. Usually when we think of infinite digits, they go to the right, like pi. 3.14159 on to the right.
That's true for real numbers, yes. Real numbers fill in the infinite microscopic gaps between integers. But p-adic numbers go the other way entirely. They are sequences of digits that stretch infinitely into the larger place values, like ... 9999 or ... 821875.
And the frozen tail we see in tetration. That specific string of stable digits we've been talking about for the last hour.
It is essentially just a finite slice of one of these infinite p-adic numbers.
So when we calculate a power tower of 3s, and those rightmost digits freeze into place, we are essentially just revealing more and more of this pre-existing infinite leftward number.
Yes. We are wiping the dirt off a fossil. And this infinite number isn't just a random string of noise. It is a precise solution to a specific algebraic equation.
What equation?
The equation is y to the power of t equals y. But in base 10, specifically, the stable tail of these tetration towers converges to a solution of the equation y to the 5th power equals y.
Y to the 5th equals y. Wait a second. If I take a normal number, like 2 to the 5th is 32. That is definitely not 2.
Right.
If I take 3 to the 5th is 243. Also not 3. The only normal numbers where y to the 5th equals y are 0, 1, and maybe -1.
In the standard world of regular integers, yes, you are completely right. But in the world of 10-adic integers, these infinite leftward strings, there are other solutions. There are what I like to call ghost numbers lurking deep in the architecture of our number system.
There's numbers.
There are non-trivial solutions. Obviously, an infinite string of zeros works, and an infinite string of zeros ending in a 1 works. But then there are the weird ones.
Like what?
There is an infinite 10-adic number that ends in ... 9, 2, 0, 7, 0, 5, 7. If you take that entire infinite number and raise it to the 5th power, you get the exact same infinite number back.
That is completely bizarre.
It means there are stationary points in the number system, attractors.
Like magnets.
Exactly like magnets.
Mm.
When you start titrating a number, iterating that exponentiation over and over, you are basically tossing a base number into a highly dynamic system. And the mathematical gravity of these padical fixed points starts pulling the number in.
And that magnetic pull is what we are actually witnessing when we see the digits freezing.
Yes. The digits lock into place simply because the number is getting closer and closer to that fixed point solution. And for base 10, there are only a handful of these solutions available.
The paper lists them out, doesn't it?
Right. It enumerates them, and every single time you build a power tower in base 10, you are inevitably sliding down the gravity well towards one of them. Which specific one you hit just depends on your starting base.
And this underlying structure changes if you change the base, right?
Yes. In base 6, for example, the equation isn't y to the 5th, it's y to the 3rd equals y. The entire invisible structure changes based on the prime factors of the base you're operating in.
So to bring this all the way back to Graham's number, that massive tail of stable digits we know exists.
It is essentially a shadow.
A shadow.
A completely deterministic shadow cast by one of these p-adic fixed points.
Yeah.
The humble number 3 is just being pulled relentlessly towards a specific infinite solution of y to the 5th equals y.
Wow.
And that congruence speed of 1, the v of 3 equals 1, that is just us measuring the exact velocity at which it falls into that mathematical gravity well.
It really makes the infinite feel surprisingly structured.
That is the ultimate beauty of it. We call it finding order in the infinite. We normally think of infinity as this boundless, chaotic, terrifying expanse, but mathematical logic actually imposes a very rigid skeleton underneath it all.
Even the monsters have to follow the rules of the house.
Especially the monsters.
So let's recap this incredibly deep journey. We started with a conceptually simple operation, tetration, the tower of power.
And we saw that despite growing to sizes that literally break the physics of the universe, the far-right tails of these numbers freeze completely solid.
We learned about congruence speed, V of A, and how Marco Ripà and his collaborators at EnigMatematica managed to quantify exactly how fast that freezing happens.
Yeah.
And they did it using the DNA of the number's prime factors.
Right. Through p-adic valuations of things like a squared plus 1, we found that V of 3 equals 1. Slow, steady, linearly filling in the digits one step at a time.
We saw how the environment itself, the radix, determines if there's any stability at all. Base 10 is safe because it is perfectly square-free. Base 16 is pure chaos because it contains a squared prime.
Square-freeness is the ultimate key to guaranteeing order.
And finally, we saw that this entire freezing process is really just a number falling inevitably towards a p-adic fixed point. A ghost solution to y to the 5th equals y that existed long before humans ever even wrote down the number 3.
It perfectly connects arithmetic, number theory, and advanced p-adic analysis into one beautiful, coherent picture.
It really changes how you look at a simple number like 3. It's not just a quantity of 3 things anymore. It is a seed with a highly specific, predetermined trajectory through the infinite.
And a very specific speed at which it travels.
So here's a final provocative thought for you to mull over as we wrap up. We constantly talk about calculating Graham's number. We talk about supercomputers churning through algorithms to find these digits.
But if the tail is entirely determined by these pre-existing p-adic solutions...
Exactly. If the tail is already there, just waiting in the invisible structure of the p-adic integers, are we truly creating these numbers when we do the math? Or are we simply discovering locations on a map that was already written on the ceiling of the universe?
Discovery versus invention. It's the eternal question of mathematics.
I think, based on everything we saw today from EnigMatematica, the map was absolutely already there. We are just finally building tall enough ladders to see it.
The structure is always there. You just have to know exactly where to look.
Next time you look at the number 3, or 5, or even just 10, remember the ghost numbers waiting patiently at the end of their infinite towers. Look at a -1 and a squared plus 1 a little differently from now on. They aren't just trivial math problems. They're the actual keys to unlocking the speed of infinity.
There is always deeper structure to find if you're willing to look hard enough.
Thanks for taking this incredible deep dive with us.
Until next time.